today is Sijie's PhD defense. He joined my group in 2019, and he's working on the geolocalization, image-based geolocalization problem. Okay, Sijie, the stage is yours. Just keep it like 15 minutes, okay?
Okay, yeah, thank you so much. Yeah, good afternoon, everyone. My name is Sijie, and I'm going to present for my dissertation defense. So the topic is toward real-world cross-view image geolocalization. And my advisor is Dr. Chen Chen, and committee members are Dr. Mubarak Shah, Dr. Yanjie Fu, and Dr. Minjie Lin. So here's my education background. I got my bachelor's degree from University of Science and Technology of China at 2015. And I got my master's degree from University of Chinese Academy of Sciences at 2018. And here's the overview of today's presentation. So firstly, I will introduce the background and the problem statement. And then I will talk about the dissertation outline. So firstly, I will introduce two real-world scenarios. So where the query can be from arbitrary locations or arbitrary orientations. And then I will introduce a transformer-based solution for all those scenarios. And finally, I will also talk about the future work. So let's start with the problem statement. So firstly, assuming that we are in a crowded city, for example, maybe in New York City, and we have a very noisy GPS, maybe have an error up to 50 meters, or maybe we are in the middle of nowhere and there's no signal at all. Or maybe we have some images from the social media and we don't have the GPS data. So basically, the question is, where is it? So we have the images as the input, and we want to have the GPS location as the output. So as for the problem of cross-view geolocalization, we have a street view image as a query. For example, it looks like this. And we want to localize it. So we want to search in this reference database. So basically, this reference database can be from street view image. It can also be from area view image. And then we want to find the most similar ones. Then we retrieve that and use the GPS of that image as the final output. So basically, this is a whole pipeline. And apparently, the street view images is very easy to match, but it's hard to collect. Like, for example, maybe some of the countries, you are not allowed to collect large-scale images, or maybe you have privacy issues. But for the area view image, it's very easy to collect all over the world, and you can easily cover the whole city. So here we use area view image as the reference, and we call this problem as cross-view geolocalization. As for the significance of this problem, so it has been proved to be useful in a lot of applications. For example, the autonomous driving, the GPS refinement, the navigation, UAV pose estimation, and the landmark matching. And so as for the previous work, as we can see here, if we have these two images, the early works, they just directly match these two images, which is not good because they look so different. And if you directly match these, you have a very bad performance. So currently, the state-of-the-art method, they come up with the idea to use the geometric prior knowledge. That is, they apply a transformation. It is called a polar transform. And to use this transformation on the area view image, then you get a similar layout as the street view image, like this. Then if we compare these two images, it becomes much more easier. So the performance can be improved significantly if we compare with the early works. But here, the number seems to be very, very high. But in the real world applications, the scenarios can be more complex. So this kind of technique may not work. So are we ready for real world use? So in this dissertation, we propose to push this task toward the real world scenarios. So the first scenario is that the queries can be from arbitrary locations. For example, we have a reference image here, And the previous works, they just assume that the query can be only at the center of this image, like the green star. But the actual location, it can't be anywhere on the street, the query. So for example, maybe at the red star. So basically in this scenario, we need to do some research. And there's another scenario that is the orientation may be arbitrary. So for example, the previous work, they just assume that the yellow bar, so both of the images, the yellow bar, they always correspond to the styles. That is their orientation or their direction, they are always aligned. But this is not always available in the real world applications. So we propose at last we propose a transformer-based solution so that it can work for all those scenarios. Let's start with the first scenario. And this work was published in the CVPR 2021. The motivation is that the existing works just simply assume that each query image can only have one corresponding reference image whose center is exactly aligned at the location of the query. But this is not practical because the real world queries can be anywhere. So basically, there is no data set in this field that can do this kind of setting. So we propose a new data set to study this problem. Here, for the arbitrary locations, what do we mean? For example, we have a reference image like this. The query can be somewhere on the street, like the red star. It will look like this, or maybe somewhere on the street like the green star. It looks kind of different. So that is arbitrary locations. But then the next question is, you have the arbitrary locations, how can we cover all these queries? The previous works, they just very sparsely sample some of the reference images, like these yellow boxes. You have the two boxes there, and they just directly assume that the query can only be at the center, then they are covered, right? But in real world case, for example, they may be at the green stars, they are not at the center, but somewhere, for example, the edge area of these images, or maybe they are like the red stars, they are even outside those images, so they are not covered. In this case, they cannot be localized. So how do we cover all those queries? We propose to do a very dense sampling with overlap so that we can cover them all. For example, we first sample here, right? And then we can sample the other one with overlap, and we can keep sampling like this. In this case, we cover the whole row, and we also do the same for the other direction. We keep sampling like this. So in this case, we cover all these queries, and we can also do the same for the whole area so that we cover them all. And this is the first attempt to cover the arbitrary query locations in this field. And another novelty is that we are also the first one to go beyond one-to-one correspondence. So what do we mean by one-to-one? For example, for the previous work, we have a query like the green star, and they assume that there is only one corresponding reference image. This is one-to-one, and it is always perfectly aligned, like the green box. But the actual reference may be like this. So it covers this query in the central area, but not exactly at the center. So it has a very large IOU with that box. So we call it a positive. But there might be some other reference like the blue box. It also covers this query. So in this case, it is not covered in the central area, but in the edge area. And it has a smaller IOU with the perfect aligned green box. So we call it semi-positive. And for each reference, we also have multiple queries, not just one query. For example, here we have some red stars in the central area. We call them positive. And we might also have some other queries like the blue stars. They are in the edge area, so we call them semi-positive. So in this case, we have multiple reference or multiple query. And we collect our data set in 4 major cities. New York City, Chicago, San Francisco, and Seattle. And we use very dense sampling so that we almost cover all those streets in this area. And the satellite image is also very densely sampled to cover the whole area. Here is a comparison with other data sets. So as we can see, our data set is the only one that can provide the arbitrary location. And it is also the first one to do the evaluation in terms of meters. And we have a thinness coverage on the area of interest. We also have multiple reference, but the other data sets, they only have one reference for each query. So after we propose this data set, we also propose a method to address this. Here, as we can see, we have two input images. This one is the street view query, and the next one is the positive every view reference. So we have those two images. And we put them into two different CNN encoders so that we can extract different features. And after we have those features, we do feature aggregation so that we can get a global feature. So at last we get one feature, one global embedding feature for both of the images. And we can train this with a simple triplet loss. That is a standard retrieval pipeline. But we have two novel contributions here. So the first one is that we introduce multiple reference. That is we add another one as a semi-positive sample. So this image also covers this query, but not at the center, but at the edge area. And we also put it into this reference branch so that it can also get an embedding feature. But it is trained with another loss, which will be described later. And the second novelty is that we have another branch after the retrieval. We predict the GPS offset so that we can have a more accurate result. So let's start with the first one. The first one is a loss function. And here, for example, we already have the embedding feature from the query. And we also have the embedding feature from the positive sample. So we can compute their similarity. It's denoted as S positive. And as we described before, I also include the other one as semi-positive. So it also have a embedding, and we compute the similarity. We also have the similarity there. And so the problem here is the semi-positive sample is neither positive nor negative. So the similarity should be somewhere between 0 and 1. And it is hard to directly assign a value. So we propose to assign this similarity with the IOU. For example, we can force the ratio of the IOU to be the same as the ratio of the similarity. For example, as we described before, the IOU of the positive sample is much larger than the semi-positive, so the similarity should also have the same ratio. And with this kind of loss function, we are able to outperform all those other configurations on this data set. Here, the same city means that we train this network and test in the same city, but different parts. But for the cross city, it means that we train in one city and we test in the other. That is totally different. And after we have this loss function, we also have the other branch. That is, we go beyond image level retrieval to a fine-grained GPS prediction. For example, we have a query here. If we only do the retrieval, then we retrieve this one. And we can only use the center of this image, the red star, as the final output, right? But the actual location of this query may be at the green star. We still have a large error there. So we want to reduce this error by directly predict the GPS offset. So how do we do this? Firstly, we have this embedding features from the query and the positive sample. We concatenate them together, so we put them together. And we just put them into an MLP, which is just multiple linear layers. And then we directly generate the offset of latitude and longitude. So the loss function is just the regression loss. And here we show an evaluation based on meters. For example, we can select 15 meters as the threshold. That means if the error is less than 15 meters, it is considered as correct. So in this case, we can compare the accuracy between different methods. So the regression-based method has a much better accuracy than the other ones, like the retrieval only and the classification. That proved the effectiveness of this branch. And we also compare our overall performance with other state-of-the-art method. Both same city and cross city, we have a much better performance than the other method. And we also showed performance on the meter level evaluation here. And it also have better performance. So here's the contribution. We propose the first benchmark for cross-view image geolocalization beyond one-to-one retrieval, which is a more realistic setting for the real-world applications. And we have a normal method with multiple reference images and fine-grained GPS prediction. And we also have significant improvement on the 10-meter level accuracy on both same view and same city and cross city evaluation. So next, I will be talking about the queries from arbitrary orientation. So this work was published in the WCV 2021. And the motivation is that in the real world scenario, the street view queries and the area view reference images, they may not be aligned in terms of orientation. And in this case, how to improve the performance or even estimate the orientation, when we don't have it. So let's start with the definition of the orientation. For example, we have an area view image and we have 4 directions. And then the 0 corresponds to the yellow bar. And if we have a panorama, it also have these 4 directions. And the yellow bar is also the 0 degree. So if the yellow bar is always corresponding to the south for both of the images, then we call it like a perfectly aligned. But for the real world case, this may not be available. So the first contribution here is that we revisit this problem in this field, which is mostly ignored by the previous works. That is, different works have different settings on this orientation. For example, some of the works, they directly assume this perfect alignment. For example, the polar transform we mentioned before and the other GAN-based method. But there are also some other works like the CVMNet or Vo and Hayes. They randomly rotate this area view image so that the orientation information is destroyed. So in this case, if we directly compare these 2 kinds of methods, it can be unfair because we don't know how much the orientation would affect this performance. So we did an experiment. And for example, we apply a standard retrieval pipeline. And we use this pipeline, we trim it with alignment, that is with orientation information. But when we test it, we use the rotate. When we say rotate, it means that we randomly rotate this area view image, just like the previous works. So in this case, the orientation information is destroyed and the performance gets much lower. So that means the orientation has a very large impact on the final performance. And in this case, since the orientation information is not available, and the geometric correspondence between those 2 images is unknown because you don't know the orientation. And the geometric-based method cannot be directly applying. So how do we consistently improve performance if we don't know the orientation? We turn to another direction, that is to improve the metric learning techniques, or for example, we can improve the loss function. So here we use a standard pipeline. For example, we have the panorama and the area view images as the input. Or maybe in some of the data set, we don't have panorama. So we use the cropped street view images. That is only part of the panorama, and also the area view image. And we put these two images into two different CNN encoders. We can get two different features. And we use fully connected layers and L2 normalization to generate the final embedding features for those two images. So here is just a standard retrieval pipeline, but the normal thing is that we can improve the matching loss function. So let's start with the predominant method. So currently, the most widely used loss function in this field is still triplet-based. As we notice here, if we have a query, so we have the feature, embedding feature of the query, and we also have the positive reference image. Then we have its embedding feature, and we compute the similarity, it will be denoted as SP, and we have a negative one reference, so we can compute the similarity. And then the most widely used loss function is called soft margin triplet loss, which is formulated like this. So here the sigma is just a soft margin function, so it's just a function, and the alpha is just a weight hyperparameter. But as we can see here, the positive similarity and the negative similarity, they are always optimized in the same term. So they always share the same weight. But this wouldn't be a problem for the general metric learning because the positive and negative samples, they are balanced. But for our task, there is a problem because our task is highly unbalanced. The positive samples are much fewer than the negative samples. As we can imagine, if we have a query, maybe only one reference is correct, it's positive. Or even if we have multiple, maybe we only have like 4 or 5, but all the other reference images from other locations, they are negatives. So we have lots of negatives, but we only have very limited positive. In this case, we propose to optimize the positive and negative samples separately so that we can better adjust and make it balanced. So we propose to do this kind of binomial loss, which we have two different terms for positive and negative samples. Here, the sigma is also, we use the same soft margin functions, but for the alpha, we have two different alpha for positive and negative so that we can adjust. And we also have another parameter called margin, M. We also have two different parameters for positive and negatives. So in this case, since the positive, we only have maybe one positive, it will be much easier to pull this sample close to the query than pulling all the negatives away because we have so many negatives. So here we show the similarity distribution of different methods. The blue ones are the distribution of the negative samples, the similarity, and the red ones are the positives. And the dotted curves, they are from triplet loss, and the solid, they are binomial loss, which is proposed. And as we can see here, for the negative distribution, they are mostly similar. They have an average value close to 0, which makes sense because they are negative, so they have a 0 similarity. But as for the positive, there is a gap between those two distributions. That means the binomial loss, they have a larger average similarity for the positive sample than triplet loss. And in this case, the positive sample and negative samples, they are separated with a larger margin so that you can easily match. So with this kind of technique, we are able to consistently improve the performance. So the performance is significantly improved no matter we have the orientation or not. So in this case, if we compare with all the other methods without orientation, our method is still the best performance, and not just the CVUSA with panorama. On the VO dataset, where there is no panorama, we only have the cropped image, our method still achieves the best performance. So after we have this performance, the next thing we want to do is to explain it. So why this model have this performance? So how this model works? So we are the first one to conduct visual explanation here to show how the model works. We use a method called gradient cam, which is first designed for classification, but we adopt it here for the retrieval. And it can highlight the most important regions of those two images, which contribute most to the final output. For example, here, these red circles, they highlight those important regions, and they are very likely to be the same object from those two images. And we have a very interesting finding here. If we train our network with randomly rotated satellite image, that is to say we don't have the orientation. In this case, the activation map becomes invariant. So no matter how we rotate it, the activation map always focus on the same region. It's always focused on the road. We can use this kind of property to estimate the orientation. So how do we do this? For example, we have two images, but the satellite image is randomly rotated. We don't know the orientation. And here we generate the gradient cam map, and we use a threshold to extract the most activated region. And then we can get the angle distribution of those two regions. So we have two distributions there. So what we want to do is just trying to shift one of these distribution to match the other one, so that we can find the best matched angle to be the final estimated orientation. And we use this method on the CVUSA, and we actually outperform those supervised methods, even if we don't have supervision here. So here's the contribution. We have a comprehensive revisiting and analysis on the orientation issue of this field. And we propose a new loss function which can achieve state-of-the-art performance without orientation. And we also propose a novel method to do orientation estimation without explicit supervision. After this work, we also have a follow-up work to have a better visual explanation and orientation estimation, which is published in the transaction on image processing. So as we can see here in the animation, we can generate more detailed explanation for each point, not just the overall image. And with this more detailed visual explanation, we are able to generate better orientation estimation than the method we proposed before. But due to the time limitation, we are not going to details, but you can check our paper if you are interested. So next, we will propose this transformer-based solution. The method was called TransGeo, and the paper was published in CVPR this year. This method is considered as a generic solution for all those challenging scenarios. So let's start with the problem. As we mentioned before, in this problem, we have two images. And the main challenge here is that we have a large domain gap between these images, so that it is very hard to directly match them. So the predominant method, they are all based on CNN, and the early works, they suffer from this domain gap. So they have a low performance there. And very recently, they are able to achieve a high accuracy because they use a technique called polar transform. And what is polar transform? So as we mentioned before, we have these two images. So the polar transform is trying to transform this area view image into a similar layout as this street view image, so that you can easily match these two. And this is the equation for the polar transform, and it assumes that the transformation is done at the center of the area view image, like the purple star. But this is not always the case for the real-world scenario. For example, here we have a reference image, and the center is the green star. But the real query may be somewhere on the street like the red star, and the query look like this. But if we still use the center to do the polar transform, what do we get? So we get some image like this. So we still have a very different layout, and we can see that it still looks quite different. If we use these two images to match, actually it gives you a much lower performance. No improvement, but lower performance. So in this case, the CNN and polar transform doesn't work, and we still want to improve performance or bridge the domain gap. So we turn to another direction. That is, we use pure transformer. We don't use CNN to do this. So as we know, the vision transformer has been recently introduced to vision tasks and achieved significant performance. And the basic idea is very simple. So you just break the image into small patches, and you can use linear projection to generate embedding for each one. And you add positional embedding, put them into a transformer, you just get the output. But this kind of architecture is very suitable for our task because it has explicit positional information. In our task, we have two different views. And if we have this positional information, we may be able to directly learn the geometric correspondence between those two views so that we don't need prior knowledge. And also, this will have the strong global attention, which have improved performance. So here's the proposed method. We have two images from straight view and area view. We break them into small patches, just like the vision transformer. And we can put them into a linear projection. We get the patch embedding for each of them. And we add the positional information, which is called positional embedding for each of them. After this, we add another one as class token, which is to aggregate the information for the final output. And then we can put these two into two different transformer encoders to learn different information. After this, we have MLP head, and we can get the final output. We use triplet loss to train it, and this is just a standard pipeline for this stage 1 training. But for the stage 2, we did something that is similar to human behavior. For example, when human beings, they are looking at this image, we want to first attend on those important regions, and then we trying to zoom in to find some details there to help you make the decision. So here we use the attention map as a guidance, and we can also zoom in. We have a higher resolution on the area view image, but here we use the attention map to do a non-uniform cropping. After this cropping, we only keep the informative regions. So the other redundancy, we can remove it. In this case, we have the same computation, but we have more details in those important regions. We use this information and we put them into the same transformer encoder. We have the shared width, and we also train this branch with triplet loss. So here's the detail for the non-uniform cropping. We have the input image, and we get into the transformer encoder. Here we have a couple of tokens. The green box, they are image tokens, but the red box, it is the class token, which is the only one connected to the output. So we use the correlation between the red ones and the green ones as the attention map, which can represent the importance of each token. And we have this attention map, and we can resize it and binarize, and we zoom in and we do the non-uniform cropping. So we only keep the important part. So we first compare the retrieval performance on VIGOR dataset. As we can see, our method have much better performance than the previous state-of-the-art method. The margin is, or the gap is almost 20%. And we also show the meter level evaluation. Here we use 20 meters as the threshold, which means if the error is smaller than 20 meters, it is considered as correct. And the performance is also much better than our previous method, even better than the VIGOR. And we also evaluate on the CVUSA, where the query is exactly aligned at the center of the reference image. So in this case, the CNN-based method, they also work very well. They also have a high performance here, but our method is still able to generate a competitive performance there. And we are also the first one to provide quantitative measurement on the efficiency. So we compare with the state-of-the-art SAFA method, and we have a much smaller G-flops, GPU memory consumption, and the inference time. So after we do the standard settings, we also want to consider the unknown orientation that is we discussed before. So if the direction of this reference image is known, like the up is north, and for the street view, the north should be the center. But we can randomly shift this street view panorama so that we don't have the orientation. And in this case, the red line, the north is not the center. And we compare with previous method, and our method still achieve a significantly better performance. That means we can generalize to unknown orientation. And the other real-world cases is that we have a limited field of view. That is to say, if we have a panorama, we have 360 degrees, but in the real-world case, we may only have half of the image, like 180 degrees, or maybe you have a quarter of this image, you only have 90 degrees. And in this case, we compare with the previous state-of-the-art method called DSM, and our method is still achieve significant performance there. So we also do visualization to show the attention map of each layers. As we can see, we have two input images. And the last layer attention map show more high-level information, so which part is more important. But the first layer attention, they only show some low-level information. But here, if we pick up the most activated patch and the compute its correlation with all the other patches, we find that it has very strong correlation with all the other patches, even if it's only the first layer. That means it has a strong global attention. So here is the qualitative result. We show three results here. The first row, the ground truth is retrieved as the top one, which is a successful case. But for the second row, it is retrieved as the second one. But the first one is still close to the ground truth. But for the last row, the ground truth is not retrieved in the top 5. But if we check the top one, it is still have a very, very small GPS error because it's kind of still near this region. So here's the contribution. The CNN-based method highly rely on the polar transform, but we propose a transformer-based method that can perform well without polar transform. And the proposed method achieves state-of-the-art performance on major cross-view geolocalization benchmarks. And we also find that removing a large portion of these patches from area view does not cause much performance drop. That means there are still lots of redundancy in this task. And we can leverage this redundancy to reduce the computation, or maybe we can improve the performance without additional